We are building our food systems on a foundation that is cracking. In major agricultural hubs, soil bakes under intense heat for months, turning rock hard, only to be hit by sudden, violent torrents of water that wash the topsoil away entirely. Our modern global breadbaskets are breaking down under two opposing extremes. On one side, we face multi-year, bone-dry droughts. On the other, we are seeing severe, unpredictable coastal flooding that swallows millions of acres of farmland in a matter of days. To fix this, we often throw massive amounts of energy and highly complex, mechanized technology at the problem. But in our rush to engineer new solutions, we are ignoring the fact that ancient societies already figured out how to grow food in these exact environmental extremes. Researchers call this indigenous agricultural knowledge, or IAK. This is a form of localized ecological engineering, where farming practices are rigorously tested over centuries to match the specific chemical and hydrological demands of a single environment. Survival in our coming climate requires us to apply the logic of two ancient systems designed for extreme environments. One conquered the flooded wetlands, and the other mastered the bone-dry desert. 600 years ago, the Aztecs built Tenochtitlan, a sprawling, densely populated metropolis, but they built it directly on top of a system of shallow, inundated lakes in the Valley of Mexico. To feed that massive population in a flooded environment, they engineered the Chinampa system. These are highly structured artificial islands built right into the shallow waters to generate massive agricultural surpluses. The Aztecs wove giant enclosures from reeds and stakes, layering nutrient-rich canal mud with decaying vegetation to form a raised bed. Because this porous bed sits directly in water, capillary action pulls moisture naturally upward into the root zone. Farmers never relied on rainfall. On top of these beds, they planted a specific polyculture of corn, beans, and squash. The beans fixed nitrogen into the soil for the corn, while the squash leaves shaded the ground to retain moisture. This created a closed, self-sustaining nutrient loop. The Chinampas operated as a self-sustaining biological engine. By constantly pulling muck from the canals and cycling plant matter, the Aztecs fed an entire empire for centuries without depleting the nutrient density of the underlying soil. Halfway across the world, we find the absolute opposite extreme. This is the rocky, bone-dry desert of Jordan, the site of the ancient metropolis of Petra, built by the Nabateans over 2,000 years ago. In a landscape this arid, survival depends on managing sudden, violently destructive desert flash floods. When it finally storms, water tears through the narrow sandstone canyons with enough force to carve the rock itself. To protect a city of this scale, the Nabateans developed an extensive, city-wide hydraulic engineering network. This system of dams and bypasses was designed to capture and control the kinetic energy of the floodwaters. They managed the entire watershed by carving precise channels straight into the canyon walls. These channels intercepted the runoff and safely redirected the water's momentum, feeding it directly into terraced agricultural plots. This 3D cutaway shows where that redirected floodwater ended up. It poured into deep, hidden cisterns carved directly into the solid sandstone. Shielded from the sun, the water could not evaporate, providing a reliable year-round irrigation supply in a place with almost no rain. The Nabateans survived by mathematically calculating the flow of the desert's most destructive forces and harvesting that exact energy to create a sustainable water supply. Today, sprawling megacities like modern Mexico City rely heavily on long, fragile, globalized supply chains. When extreme weather disrupts a distant harvest, the shelves in these concrete hubs go empty. Yet inside the city limits, sections of the ancient Aztec Chinampa network are actively functioning today. They serve as a highly localized food lifeline, operating completely independent of global shipping routes. We are now seeing a new scientific synthesis emerge. Agronomists are combining these ancestral, organic structures with modern digital networks and machine learning systems. This diagram illustrates how modern technology maps on to the ancient framework. By embedding smart sensors and IoT directly into the soil and water channels, farmers can monitor exact moisture and nutrient levels in real time. IoT refers to the Internet of Things, a network of physical objects embedded with sensors and software that exchange data over the Internet. This approach provides the foundation for food sovereignty. Food sovereignty is the right of communities to control their own food and agricultural systems, shifting away from vulnerable, monolithic industrial farming towards resilient, hyperlocal food networks. We do not have to choose between the past and the future. Achieving agricultural resilience in the 21st century requires us to adapt to our local extremes by marrying traditional ecological wisdom with precision science.